This video is an example of how to use Green's theorem, the circulation form, to go from a line integral to a double integral. So that's the connection of Green's theorem. The first thing to notice in the circulation form, the idea is you've got a vector value function on your space, and you have a closed curve that encapsulates that covers a region D. The line integral calculates the total amount of circulation around that closed curve by taking the dot product of the vector field with the derivative of the curve described by the vector value form. So the first step for writing a problem like this is to draw out the curve and see if it does the bounded region. This is telling us it should be a triangle that's oriented counterclockwise. I plotted the vertices in GeoGebra and shown the triangle as a curve. So there are a few things going on here. The region is this region D, and the curve is broken up, oriented into segments, a C1, a C2, and a C3. If you were going to do a line integral version of this calculation, you would have to give a parameterized curve for each of these pieces, and it's just easier to break it apart one piece at a time. So you give a line, the vector form equation for this particular line, horizontal line, this vertical line, and this hypotenuse. We're not going to do that in this case. We're going to do double integral. In order to do that, we have to give an orientation. It's supposed to be counterclockwise, and what that means is you take a point inside your disk, so this point over here, you can see a counterclockwise direction is this part of a circle over here, this arrow. And notice that this counterclockwise arrow touches the curve. It should have the same orientation. The curve should have the same orientation as this counterclockwise turning over here. So if you choose a point inside your region, the arrow should go the same direction as the circle touches the boundary curve C1. Notice that it should be going the same direction in C2 and in C3. With the curve oriented and the region labeled, we're ready to move on to trying to apply the formula. In order to apply the formula, we have to figure out what is the actual vector value function from the way it's presented. And that's actually not too hard. If you look at this sort of dot product, that really just means it's the x component of the vector times the x component of the r, which is this dx, and the y component of the vector times the dy, which is this piece over here. After identifying what's the x component and the y component of the vector value function, the formula says, okay, take the partial derivative of the x component and the y component, but just switch it up. So the x component partial derivative should be with respect to y, and the y component of the vector value function's partial derivative should be with respect to x. So p partial y, since there's no component of y over here, is actually equal to 0, because x is considered a constant. Q partial with respect to x, well, there is an x over here that treats like a regular derivative, and it's just a 3. Green's theorem says now substitute those calculations in according to the formula. Now we reduce the problem to a double integral, and in this case I'm just going to do rectangular coordinates, and I'm just arbitrarily deciding to integrate with respect to y first. So I have to use the graph to figure out my limits of integration. If I'm integrating with respect to y first, I want to think about my boundary curves in the y direction. So I have curves all around, but to visualize what's happening, I can think of my dy's as stacking in a fixed x direction, dy's. So fixed x, stack the dy's, going from bottom to top, and if I do that, I notice the first curve I encounter at, or I start at, happens to be this bottom curve over here, and that's when y is specifically equal to 0. That's the equation of this particular curve with respect to y as a function. As I go up, I get to the last curve over here, and this curve is the slanted line. It's the hypotenuse of this triangle. If I need to know the equation of this particular line, well, I know how to find equations of lines. It's just the slope of a line plus the intercept. Since I know the coordinates of these points, those things are easy to calculate. For my first integrand, my limits of integration goes from 2 to y equals this equation for the line. My x, though, I project this triangle onto the x-axis and realize, well, my x coordinates for this entire region starts with a -1 and ends at a +4. I just get those from my points, the points that I have. The last step would be to actually do the double integral, but this one isn't too bad. When I take the integral with y first, with respect to y first, I don't see y here, I just see the constant 3, so just give me the y variable, then I evaluate my limits of integration. So this will just be a y, and I plug in the upper limit minus the lower limit. Sorry, I made a mistake. I forgot to distribute the slope onto this +1 term, which would have changed my limit of integration to this appropriate number, and this appropriate number over here, and I did the arithmetic in my head. You can double check to see if I made a mistake. And then you can finish up this integration.